Hi. Now we're going to see electrical conductivity in semiconductors. Before this, we have seen the electrical conductivity in metals and how we have seen how it is depend on the carrier concentration and then charge and its mobility. Now we're going to see the electrical conductivity in semiconductor. So for that purpose, let us consider a sample of semiconductor across which DC potential source is connected. That is, we have taken a semiconductor sample and connect battery across it. So potential difference is applied across that semiconductor. See this diagram. In this diagram, it is shown this is semiconductor material, and across that its length battery is connected, so potential difference is applied. And we know when we apply this potential difference, due to that potential difference, current flows through that material, and electric field which is generate, which is along the dimension of applied electric potential. So here also E is equal to V by L. If observe inside the semiconductor, you can see there is the electrons moving towards positive terminal of battery, while holes are moving towards negative terminal of battery. So total current in the semiconductor is due to the electron flow or current due to the electron plus current due to the holes. This addition of these two gives the total current. That uh, we use the term is total conventional current through the semiconductor, which is I suffix E plus I suffix P. Okay. If potential difference is applied across semiconductor, it generates electric field, which is potential per unit dimension. In this case, this electric field is V per unit length. This causes electron to move in positive terminal and holes towards negative terminal. That we have already seen. The electron is moving positive terminal while holes are moving towards negative terminals. So before to see the derivation or equation of this, we should know this terminology or these symbols. So let V is applied potential difference, E is electric field which is generated due to applied potential difference, then capital I is the total current passing through semiconductor, then I suffix E is the current due to electrons drift in conduction band, or in short we can say I suffix E is current due to the electron, then I suffix H is current due to holes drift in valence band. In short we can say this is the current due to the holes, movement of holes. Here again see there is I suffix E and I suffix H. Sometimes it is also written as I suffix P, because it is the positive is considered, and E, this electron, we already know electron is negative charge and the absence of electron is holes, so that time we are just considering it is a positive. Okay, then V suffix E is the drift velocity of electrons, while V suffix H is the drift velocity of holes. Then N suffix E is the concentration of electron, so N suffix H will be the concentration of holes. So again we'll see the total symbols that are we are using in the derivation or to obtain the equation of conductivity in semiconductor. So just again we'll see there is capital V, E, capital I suffix E, I suffix H, V suffix E, V suffix H, N suffix E, N suffix H. These are the symbols used in next equation. So first we can write the current due to electron, which we have seen in previous derivation. So I suffix E is gives the current due to the electrons. So I suffix E is equal to N suffix E into small e into capital A into V suffix E. Again see, this I suffix E gives the current due to the movement of electron. N suffix small e is concentration of electron. The small e is the charge. Capital A is cross section area. V suffix E is the drift velocity of electron. Similarly, the current due to holes is given by the equation I suffix H is equal to N suffix H into E into capital A into V suffix H. Again see here, this I suffix H is current due to hole, N suffix H is concentration of holes, small is the charge on holes, then A, capital A is the cross section area, V suffix H is drift velocity of hole. If you observe here, then small e here and here both are the charges. Why these are similar? Cause we are not considering holes as separate, cause holes is nothing but this absence of electron. So due to the absence of electron, whatever the cavity is produced, that is the holes. So the charge on both will be same. Now we get the current due to electrons and current due to holes. So the total current I we can write as addition of these current due to electron and current due to holes gives the total current passing through a semiconductor. Now we'll substitute this value in this equation. So total current I becomes N suffix E into small e into capital A V suffix E plus N suffix H into E into capital A V suffix H. This is the total current passing through a semiconductor. Now, in this equation, what are the common terms we'll take separate? So, in both equation, small e into A is common. So, we take side. So, in these remaining is N suffix E V plus NH and this VH in the bracket. Now again we know mu E and mu H are the mobilities of electrons and holes respectively. So instead of these drift velocity of electron and drift velocity of hole, we can write the equation as mu suffix E, that is mobility of electron, is V suffix E upon capital E, that is the drift velocity of electron upon electric field, and mobility of hole mu suffix H is equal to V suffix H upon capital E. So we'll put these values instead of drift velocity. So drift velocity is becomes V suffix E, that is the drift velocity of electron, is equal to mu suffix E into capital E, that is mobility of electron into electric field. Similarly, drift velocity for hole is mobility of hole into electric field, which is generated in the semiconductor. So by using these two terms, this equation of current is we can write as I is equal to the small e into capital A as it is. Then this complete bracket we can write as it is, only instead of v suffix e and v suffix h we are going to put the value of the drift velocity. So the current I gives e into capital A n suffix e into mu suffix e into capital E plus n suffix h into mu suffix h into e. These mu suffix h into e and mu suffix e into capital E are the drift velocities. So again this equation, this capital E also a constant because it is electric field which is generated in semiconductor. It will be same, we'll take its common. So current becomes small e into capital A into capital E in a bracket n suffix e into mu suffix e plus n suffix h into mu suffix h. Let this equation number 1. The total current density is J is given by the equation J is equal to I upon A, where A is cross section area. So this J is current density. It is moment of current per cross section area. So we can write this J is I by A. So the previous equation number 1 divided by A. In numerator and denominator, this A is common. We can cancel it. So J will be remain as J is equal to small e into capital E in bracket n suffix e into mu suffix e plus n suffix h into mu suffix h. This is equation number 2. Then if sigma is total conductivity, then we can write uh, by modified Ohm's law, or we can say vector form of Ohm's law, which is J is equal to sigma E. Now both are the equation of conductivity, both are the equation of current density, just equate it. Then we can write by comparing equation 1 and 2, sigma is equal to E in bracket Ne mu E plus Nh mu H. So this expression gives the electrical conductivity of typical semiconductor. In general, it is linked to the variation of mobility with the temperature is too small, and the large variation in electrical conductivity is because of large variation of electrons concentration with the temperature. Now by using these equation number 4, which is sigma is equal to E n suffix E into mu suffix E plus n suffix h into mu suffix h, which is the conductivity in semiconductor, we can apply these for specific conditions like intrinsic semiconductor and extrinsic semiconductor. We know in intrinsic semiconductor, number of electrons and holes are same, while in n-type semiconductor, there are large number of donors, and in uh, p-type semiconductor, there is large number of acceptor. That we'll see in next part. Okay, thank you.